Okay, welcome back to the next video. In the previous video, we have seen the energetics of homogeneous nucleation, and in this video, we will see how the energetics varies for the heterogeneous nucleation. This video actually, in first, we will just see the physical comparison between a homogeneous and heterogeneous nucleation once again, and after that we will we will see the energetics of or the free delta or the free Gibbs energy, and after that we will see the obstacles which is for homogeneous and heterogeneous nucleation, and we will compare and we will see which nucleation is easy to form or which one is more common and all. Okay, let us begin. Now let's once again see the homogeneous nucleation. Homogeneous nucleation, we have seen that it's unaided by any surface or defect or a foreign bodies, because it is pure thing, like any foreign bodies is not there, any like wall surface or alien surface is not there, so it is exclusively formed within our our liquid. Okay, so we have seen the mathematical calculation, we have seen that it is very simple, and it is an ideal case, like it is very rarely seen. Okay, in most of the cases the nucleation which happens is just a heterogeneous nucleation. Okay, now let us see what is a heterogeneous nucleation look like. So it is more reality, or in a more real case we will have this heterogeneous nucleation, and it is more common, and like it will originate from some some impurities. If there is any impurities there, it will immediately nucleation will happen around that one. But here like or the wall surface. So for the present study, we are taking that particular condition, that the wall surface nucleation, heterogeneous nucleation which happens on the wall surface. So here this is the wall, and here inside a liquid phase is there, and in the wall, okay, we can see a small portion of a sphere, not full portion, a small portion, we will call it as a cap is happened, and the heterogeneous nucleus just formed here. Now let us see how an heterogeneous nucleation will happen and all. Okay, so it will be aided by some surface like this, or some grain boundaries, we can say some grain boundaries in the material science point of view, or the metal point of view. In the grain boundaries will act as some heterogeneous nucleation sites, and defects can also act as a heterogeneous sites by the impurities can also act like that. So one thing I want to tell here, it is that it is mathematically highly complex. It is not that much easy as that of a homogeneous nucleation. Okay, so now let us see that portion. Let us magnify, or let us concentrate this portion much into detail. So this portion we will say like this. Initially there will be we will say there are three phases totally here. First one is a alpha phase, which is a liquid phase. We can also call it as a liquid phase, and for the time being we will represent it as a alpha. Okay, and here the second stage is the beta phase, or we will call it as a solid phase in other terms, so beta. So what is happening is that the alpha phase is converting into, or getting converted into, a beta phase, and we will have a spherical cap on we will get a spherical cap here, and while plotting we can imagine that it is of a full radius. Okay, total of radius r, and the remaining, or the only portion which we can see above the surface is this one, this cap, and there is a substrate or the wall. Okay, we have seen this wall. Okay, this wall portion is of different material, and we will call it by the term delta, or the substrate is delta. Okay, so in general we can tell that the alpha is transforming into a beta phase, on the substrate delta. This is what the heterogeneous nucleation is all about. Okay, and here we can see that just consider the surface tensions. We have seen there are two components which affects. First one is the volume and second one is the surface tension. Okay, now see the surface tension, how it will be there. Okay, here actually there will be three surface tensions. We can say there are three surface tension. The first surface tension will be between this alpha and the delta, or the liquid phase and the our substrate or the wall delta. So that surface tension part is known as gamma alpha delta, which will act in this direction. Okay, and we can say that the contact angle for this nucleus is theta. Okay, please see this figure and please keep it in mind, like this is theta. This is very, very important for our derivation purpose. Please have this concept. So this is known as the theta, or this is the contact angle. Okay, so there will be a contact between our alpha phase and a beta phase. Okay, as we have seen in the solid liquid interaction in homogeneous nucleation cases, like here we have an interaction between alpha and beta, or with a liquid and a solid interface we will call. So the surface tension which deals with that one is gamma alpha beta, and a third one will be there, that is between the surface and the solid portion which is occurring. So the surface tension for that particular thing is denoted by gamma beta delta. Okay, so the first one is between the substrate and the liquid, second one is the solid and the liquid, and third one is solid with the surface. So three will be there, and on resolving we can clearly see that the gamma alpha delta will be equal to gamma beta delta on this direction, and when to the cos component, by we can resolve this gamma alpha beta to this direction, we will get gamma alpha beta cos theta. Okay, so this is a thing which we will get, so please keep this thing in your mind. Okay, now we will see the volume part. Okay, but here in the homogeneous nucleation, like we can see that it is actually happened within the solid, so no boundary or no foreign material is there, so just like it is fully happened on within inside. So the full volume we have considered, but here we cannot consider the full volume. Here only a portion of this sphere only we can consider. Okay, we will call just as a cap, not even the half portion, just a small portion, and that this portion actually depends on this factor, that is the theta, or the contact angle. So the volume of the sphere here we will represent it as V beta. Beta represent the solid phase, so V beta will be equal to 4 by 3 pi r cube, which is the volume of our thing, multiplied by S theta. S theta is a factor which depends on the theta. Like as theta changes, we can say that this particular volume, okay, this particular volume changes as theta change. So this is calculated from some other calculations. Just for the time being, just understand that S theta is the value of S theta is this one. Okay, 2 minus 3 cos theta plus cos cube theta by 4. Okay, so if we plot the value of S theta for various thetas, like from theta ranging from 0, like see theta ranging from 0 to 180 up to here, from theta value ranging from 0 to here, we will get the value like this. So S theta is a factor, like it varies like this. Okay, for all the thetas ranging from 0 to 180, we will get the value from this curve. Okay, so coming back, now let us focus into the surface areas. Here we need to consider two surface areas. That is, the first one is the portion of the cap portion we will call, that is between the alpha and beta. So that is the cap surface area we need to consider. And second is the surface area. Another surface area is between beta and delta. which will be this one, this portion. If we just check the top view, we can see that this portion will be circular. Okay, will be a circular one on the top view. So imagine that condition and just see this one. So alpha beta, which is this top portion, will be equal to 4 pi r square, and it's a factor of theta as we mentioned earlier, and is taken as 1 minus cos theta by 2. Okay, so the surface area of this one will be 4 pi r square into 1 minus cos theta by 2. Okay, now second one is this circular portion. Again we can say that we cannot say the value. This area is also dependent upon this particular contact angle, because it will vary with this contact angle, and it is taken as pi r square into this particular area, which if we just see from the top view, okay, just imagine a top view, then we can see that this particular portion will be a circular one. So it will be pi r square into 1 minus cos square theta. Okay, and now just calculate, and we know the free energy heterogeneous, this Gibbs free energy, heterogeneous free energy, change in the Gibbs free energy, heterogeneous, will depend on two factors, that is the surface energy, which depends on the surface tension and the area, and another one is our regular one, that is the volume to the force energy, force per unit volume. So we will write this one as V beta. This is the volume of the surface, which is taken from here, V beta, into the G beta minus G alpha. Okay, G beta is the free energy of the beta phase, and G alpha is the free energy for the liquid or the alpha phase. So we will say that it is as discussed in the homogeneous nucleation. This is the driving force here. And here surface energy, earlier portion we have seen only one surface in energy, that is the solid liquid interaction, but here we have three surface energies. So A alpha beta into gamma alpha beta will be there. That is the first interaction. This is the first energy, second energy, and third energy will be there. And second will be A beta delta. Okay, A beta delta, this one, A beta delta into gamma beta delta, minus the third one is there. This is very critical, that is this one I have written as, it's not clear, but please note that it is beta delta. Okay, A beta delta into gamma alpha delta. I will tell you the reason, but in fact it is A alpha delta into gamma delta. Okay, this one, A alpha delta, this one alpha delta into gamma delta. That means this portion. Why I have written the beta delta is that the explanation is given here, you can refer that one, but why I have given it beta delta is that this area beta delta and the beta alpha delta is same, because you can see that there will be the area between the beta delta. Previously, before this beta phase is formed, this portion is taken up by the alpha. So it was alpha delta was replaced by the area beta delta. So we don't need to just calculate it again. That means this area alpha delta is same as that of area beta delta. Okay, so we have changed, the explanation is here, you can refer. So we have replaced it by beta delta. So this is again we can say a minus sign is given. Why a minus sign is given? Because you can say that we can see that the area is replaced. Okay, this area is replaced by beta phase, so we will give a negative sign to here. So again this portion will act as a driving force. So this portion we have seen it is a driving force. Along with that, this portion will be a driving force, and this will act as a barrier. Okay, so in general delta GF is fully of function of r and theta, since all the portions or V beta, this one, all the things are the functions of radius and the theta contact angle, so it will be a function of r theta, and there we can see that the maximum at maximum here also at maximum dou delta G heterogeneous by dou r maximum, the value will be 0, and r at the radius at which the nucleation begins is known as r star heterogeneous. Okay, and there is a solution is there. Those who are interested can solve, but the answer you will get it like -2 gamma alpha beta by delta gv, where delta gv is this particular thing, gb minus g alpha. Okay, so you can understand that you can just get this thing, and okay, and we can see that here the value here we got the value as r heterogeneous, and on solving you will get this value. So this is this value we will represent it as r star heterogeneous, and the value we can see that the previous value it is same as that of the previous value. Okay, that alpha means it's our liquid, and beta means our solid phase, so it is just same as that of our previous liquid solid interface by delta Gv. So that means the radius or the critical radius here will be same as that of the homogeneous and heterogeneous nucleation. The critical radius will be same. Okay, at a particular point this will happen, and but only difference is that the volume of the nuclei is different. At the volume of this nucleus formed is different for homogeneous and heterogeneous. And in general we can write the volume of the heterogeneous nucleus as the volume of homogeneous nucleus into S of the theta, okay, multiplied by S of theta. And we can say that as theta increases as theta comes down, the value of the theta comes down, the volume of the heterogeneous nucleus also comes down. That means S of theta is please see this graph. As theta comes down, the S of theta value is also coming down. So we can see that here the heterogeneous volume will come down. That is, the volume of the heterogeneous nucleus will always be less than that of the volume of homogeneous nucleus. Okay, smaller the theta, smaller the S value. Okay, so please keep it in mind that for nucleation or the nucleus growth or the crystal growth, so the smaller thing is much favorable. Okay, and we can see that there is a graph. If we plot the graph, we can see that this is the homogeneous nucleation curve. The free energy for the homogeneous nucleation curve goes like this, with the R, with variation of the R. And if we plot the heterogeneous nucleation, okay, we can see that the curve will be look like this. That means both the peaks will be at the same point. That is, R star of the homogeneous will be same as that of the R star of the heterogeneous. That is the peak, because the maximum point for the homogeneous nucleation is this, and the free energy of the maximum point is this. So heterogeneous also, the maximum point will be like this at this point itself, at same radius. But what we see, what thing we want to understand is that the barriers, okay, barrier for the heterogeneous nucleation is somewhat nearly half of that of homogeneous nucleation. Okay, in other sense we can say that the heterogeneous nucleation is much easier to take place than homogeneous nucleation. Okay, that's what I explained here. So that's all. Like the delta GF for the heterogeneous will also be a function of S theta, like delta GF of homo multiplied by the S theta from this from this one we can understand that thing. Okay, so like this is all about the heterogeneous nucleation, and from the study we understood that heterogeneous nucleation is most popular and most in the real time it will be the most feasible nucleation, and the surface and impurities will act as the center or the point of this nucleation, and if we remove it, this nucleation can be controlled, or the crystal growth can be controlled. And but in comparison to homogeneous nucleation, which is somewhat more ideal case, the heterogeneous nucleation is most common, and the reason is this one: the energy barrier for heterogeneous nucleation is much lesser than that of the homogeneous nucleation, and the free energy required this one for the heterogeneous is somewhat like it is a function of s theta times of delta gf of homogeneous nucleation. So that's all for this video. Thank you for the thank you for attending.